I'd like to introduce Eric Ferrebee. He's the Senior Director of Technical Services for the American Concrete Pavement Association. Eric's been in industry here for well over 15, he's been in the position for well over 10 years here, but been running around, has his master's degree in civil engineering from University of Illinois in Yeah, okay. So, yeah, Eric's very akin to running all around the country and talking pretty much all the technical aspects on concrete here. So, without further ado, we've got Eric Ferrebee.
All right. Good morning, everyone. I love that, like we're all on one side of the room. It's like in church when everybody's just sitting in the back, except we've just kind of reversed how things are. So, I'll try to talk to you guys a little bit, but like everybody's over here, so apologies. All right, so we're gonna start off the morning and kick things off fairly simply with concrete. So Brian mentioned that, this whole morning we've got sessions that are covering all different topics on concrete pavements. We're gonna kick things off very simply with concrete jointing 101. And so some of this may be extreme review for you and very basic, but we will get a little more complicated as we go through because concrete jointing is really essential to getting good performance out of our concrete pavements. And so some of this is very basic, but it will build to a point where we have to understand how to joint things such that when we have complex geometries like intersections and roundabouts and stuff like that, we can get good performance even with those geometries. Because when we think of concrete, concrete likes to be square. Even if you're looking down here, at the floors and stuff, concrete always tends to like to be square, rectangular as much as possible. Otherwise, we get cracking. So let's jump right in here. I always like to start this talk off with why do we joint concrete in the first place? And we joint concrete for a number of different reasons, but the biggest reason is concrete shrinks. This happens through a number of different mechanisms, but no matter which one it is, concrete is going to shrink over time. And the shrinkage itself isn't really a problem. If we just had concrete and we placed it on a frictionless surface like Teflon or ice or something like that, it's not going to be a problem because concrete can freely expand and contract. But we place concrete pavements on a subbase or a subgrade or something like that, and that's going to cause restraint. So as concrete tries to expand and contract, it's restrained from doing so. And when we have that restraint, it builds up stresses and then we get cracking. And so we really place our joints such that we can control where that cracking happens. And so if we didn't joint our concrete pavements, initially we would get a crack every 40 to 80 feet or so, and then over time it would get down to about every 15 to 20 feet, and you'd start to see that pattern. So instead of having something like this, we place joints in our concrete such that we can control where that cracking happens, and joints tend to be a lot easier to deal with and maintain than having random cracking all over our pavement. Now, there are a few other reasons that we joint concrete pavements. We want to be able to divide the pavement into construction lanes. This is especially important as a lot of times we're reconstructing things and trying to keep certain parts of the concrete or certain parts of the pavement open to the public. And so dividing it into construction lanes can be very helpful. We want to make sure that we can continue to accommodate slab movements. After that initial shrinkage happens with our concrete, it's going to continue to expand and contract over time. And so we have to make sure that we allow that to happen. And as that happens, we also want to be mindful of long-term load transfer. So putting dowel bars in our pavement to make sure we can maintain good load transfer over time is another ideal reason why we joint our concrete pavements. And then if we're sealing our joints, providing that sealant placement is important as well. Now, one thing that jointing is not necessarily for is lane delineation. So a lot of times we'll have those longitudinal joints match up exactly where our lane lines are, but that doesn't necessarily have to be the case. So you can see here in this example where we've actually got our joints right in the middle of a lane, and that's okay. That can work just fine. We just want to make sure that we keep those joints out of a wheel path. If they're in a wheel path, that's where we can tend to have a little bit of an issue. Now, our types of joints. We're going to go through this very briefly, primarily because it does impact how we joint complex intersections. So our main types of joints are our contraction joints, which are our sawed joints, our construction joints, and our isolation joints. We do have some specialty jointing that will happen either at transitions from concrete to asphalt or sections of concrete to different concrete, or terminal joints if we're doing continuously reinforced concrete pavement. But 95 to 98% of our joints are going to be those first three: contraction, construction, or isolation joints. So our contraction joints, again, are our sawed joints. These are going to either be doweled or undoweled. If we're at about 8 inches or more, we're going to put dowel bars in there. 7 to 8 inches, we might use a dowel bar. If we're less than 7, we're likely just using aggregate interlock to get our load transfer there. Longitudinal contraction joints, a lot of times we're going to have a tie bar in there to make sure that that joint doesn't open up over time. But again, this is happening on the longitudinal joints, so a lot of times we'll cut these a little bit deeper than we would with a contraction or with a transverse contraction joint, primarily because we're not as concerned with load transfer across a longitudinal joint. At transverse joints, we're very concerned about that load transfer efficiency. Longitudinal, we're not as concerned. Our next joints are our transverse construction joints, and these are also known as headers. You can see we've got a nice flat surface on these joints, so we're almost always going to put dowel bars in there to make sure that we get good load transfer at those joints. Otherwise, if we just had a flat surface next to a flat surface, there's not a whole lot of friction there to make sure that we get good load transfer long term. So a lot of times we are going to put a dowel bar at these joints. And there are a few different ways that we can do this, whether we're doing some hand placement or as we're doing a hand placement up to the end, or in some cases, if we're using slip form paving, we might pave through our head of concrete, which I think is my next picture. Might pave through the head of concrete and then come back in, saw that off and take it off, and then start the next day's paving right there. You can actually see where this contractor put something underneath that section of concrete so it's easier to tear up, and then we can start and pave on the other side of that joint. If we do something like this, though, we're going to be drilling in our dowel bars after the fact to make sure that we get, again, load transfer into that next section of concrete. And so our next type of joints are our longitudinal construction joints. Again, a lot of times we're going to have a tie bar there trying to make sure that that joint doesn't open up over time. You can actually see that we've tried a few different things. There's actually a keyed joint in there. So keyways is something that has been tried over time. The theory here is that if you have a keyway, that it can help kind of have some load transfer from one side to the other. So it can work reasonably well if we've got a fairly thick pavement, say 10, 11, 12 inches. But in a lot of cases, it can be difficult to construct. As you can imagine, it can be difficult to get proper vibration in there and actually consolidate that concrete, especially in those sections that kind of jut out there. So it may not work well long-term over time. Additionally, we've seen a fair amount of issues in the bottom right picture where that top section, if it's too thin, can actually just shear off. And so there you're just kind of creating a little gap that's not going to be good for long-term performance either. So keyways can still work. We still see them used in a number of different locations, but overall we don't see them being used regularly everywhere. So kind of moved away from that practice. All right, our next type of joint is our isolation joints. And our isolation joints are really trying to isolate a section of pavement from a structure or another section of pavement. And so there are a number of different ways that we can do this. You can see we've got a thickened edge joint. We've also got a sleeper slab in there. In some cases, if we do want to have a dowel bar in there for load transfer, that can happen. But in those cases, we want to make sure we have an expansion cap on that dowel bar such that they can move a little bit more freely than they would if they didn't have that expansion cap. So we use these types of joints in a lot of places, especially around fixtures or inlets or manholes that we have within our concrete pavements. And if they're done well, we can get really good performance out of them. In some cases, like over in Colorado, they will actually use these isolation joints every 500 or 1,000 feet, kind of similar to the concept of an expansion joint, which isn't really something that is built everywhere across the country. Okay, and there's just a close-up of that isolation material. We'll actually see something like that as we talk about roundabouts towards the end of the presentation here this morning. And so I always like to make mention that, and from ACPA's perspective, from national industry's perspective, we like to differentiate isolation joints from expansion joints. So expansion joints are what we would think of coming up to a bridge approach where you've got a 3 or 4 inch expansion joint. It's not the same thing when I'm talking about an isolation joint. With an isolation joint, I'm basically talking about 1/2 inch to 1 inch that's really just separating 2 sections of concrete and trying to create some isolation for some isolated movements. Okay, there are a few specialty joints, as I mentioned. Most of these are transitions from one section of concrete to another. And so a lot of times we're going to have a free edge on our concrete, so a lot of times you're going to see something that's like a thickened edge, trying to, again, minimize the deflection as we go across that joint. And so you can see a few different ways that we've tried this to try to smooth out that transition as you go from the concrete to the asphalt. And this is a place where we've got to take special attention to make sure that we can get a good, smooth transition and try to maintain that transition as best as possible. All right, so next, we got to talk about load transfer. So I've mentioned this a little bit, but load transfer, a lot of times, we're going to focus on dowel bars, making sure that we get that mechanical transfer of load from one slab to the next. But if we're in a thinner pavement, if we're, say, 7 inches or less, we may rely on aggregate interlock. And so for aggregate interlock, you can see that picture there where you've got that saw cut going down about 1/4 of the thickness of our pavement. And then from there, you're going to have that aggregate interlock that bridges that crack. And so that can provide load transfer for a while. But as you can imagine, concrete's going to continue to expand and contract. And over time, you may get separation or wear down of that aggregate interlock. And so it will provide load transfer for a while, but if you've got significant heavy trucks out there, it's probably not best to rely solely on aggregate interlock. That's why we have dowel bars. And so typically, again, dowel bars will be used anywhere from 8 inches and above, and occasionally between 7 and 8 inches. In some industrial facilities, we will use dowel bars even down to 6 or 7 inches too. But I should note that tie bars, when we place tie bars in a concrete pavement, it is not to transfer load. Tie bars are in there to keep joints tight. So on our longitudinal joints, they're not going to transfer load across that joint. They're literally just going to keep those two sections of concrete together nice and tight. And you may get some load transfer from the friction that happens between those two slabs, but it's not coming from the tie bar. And then the last thing that will kind of provide load transfer is the sub-base support. If you're on a really stiff sub-base, it's not going to deflect as much, so it will show up in load transfer efficiency that your pavement isn't deflecting quite as much. Okay, so aggregate interlock, as you can imagine, as that load transfers over there, you can see it bridging the gap. So the shear between those aggregate particles is really what's going to help transfer the load, and that's what can wear away over time. So as I mentioned, around 7 to 8 inches is where we will kind of transition from relying on aggregate interlock to having dowel bars, but that corresponds to about 80 to 120 trucks per day in terms of traffic. And so if we don't have that, you can see the difference between if we have a just construction joint where we don't have any load transfer to a joint where we have full load transfer 100%. That's why we have dowel bars in there. When I talk about this, I do like to mention that relying solely on the kind of term of load transfer efficiency is probably not a good practice. Because as you can imagine, if we have a very small deflection in here, load transfer efficiency could be very low because the differential deflection could kind of lie to you in terms of how good that load transfer efficiency is. So what we really need to look at is load transfer efficiency and total deflection, or deflection across that joint. And so looking at those two in combination is how you'll understand how well your joints are actually performing. All right, so we've got our dowel bars in there, and we'll talk a little bit about construction as we go through here as well. As I've mentioned a couple times, if we have a pavement that's 8 inches or thicker, we're almost certainly going to be using dowel bars in there to make sure that we get that long-term load transfer. If we're less than 7 inches, it's probably not necessary, but it can be used. And if we're greater than 10 inches, we're going to have a slightly larger dowel bar to kind of match up with the thickness of our pavement. Now, dowel bars is something that's kind of evolved very significantly here in the last 10 to 15 years. We've had a lot of different materials come out, a lot of different dowel geometries. You can see a few different versions of this where we've got, say, a fiber reinforced dowel bar. Up there in the top left, we've got our conventional green epoxied steel dowel bars. We've also got that bottom left picture, which is kind of an O dowel. It's a hollow dowel that's kind of increased the size of it, but it's hollow inside, so it's a very light dowel bar, but it still transfers load very well. And then we've also got zinc-clad products as well. So a lot of different dowel bars have been kind of explored here in the last 15 years or so. And just recently, AASHTO has kind of approved a new specification for testing and accepting dowel bars that kind of allows different materials and allows evaluation of these different materials as well. So, regardless of what kind of dowel bar we're using, this is kind of what we're looking for. That dowel should be totally encased in concrete, and you should have proper consolidation around it to make sure that it's actually going to be able to transfer load. If we don't have good consolidation around that dowel bar, it is a place where we can start to fail our joints fairly quickly. So we want to see good consolidation to get good performance. All right, so let's actually go through some construction considerations. So as we're building our pavements and constructing our joints, it's really important that when we have steel within our pavement, it's placed at the appropriate location and it stays there for the entire process of paving. And so you can see here where we've got some steel within our pavements. Keeping that where it's supposed to be is really important. And so when we place steel prior to paving, if we're using dowel baskets or something like that, we want to make sure that we have enough fasteners, whether they be stakes, which you can see in the top left, or these little clips that clamp it onto the pavement grade. We need to make sure that we have enough of those there that it's going to withstand the process of paving. There's also been some other things that have been tried. In that top right picture, you can see there's a little brace there that's kind of rotated into the direction of paving, and that can kind of help provide some rigidity to the basket. Additionally, you'll notice on the top left picture, they've actually snipped the shipping wire, and that shipping wire is kind of something that helps provide some rigidity to that basket. So we don't really recommend cutting that shipping wire. We recommend leaving it intact because it can actually provide some rigidity to that basket. The only reason to cut that shipping wire is such that you can use the MIT scan to actually image where your dowel bars are. But even with the new MIT scan, you can actually image the dowels with leaving that intact, which is, again, important for basket rigidity. And so this is a diagram from an FHWA tech brief from a few years ago that kind of shows mapping out where you should place those fasteners. So a lot of times we'll use 8 fasteners for an 11 or 12 foot basket. And they should be placed on both sides of that basket to make sure that, again, we're having proper rigidity and fastening to that basket such that it'll withstand those stresses of paving. And so this is what we're really trying to avoid. So this is a good example where either we didn't have enough fasteners on that basket, or more than likely what happened was as the slip form paver was going over that basket, it was too close to that edge, and then it just clipped it and brought it along with it for a little bit. And so obviously these dowel bars are not going to provide any load transfer for us. They're not going to really cause much of an issue beyond that, but they're not going to do their intended purpose. So we want to try to avoid that as much as possible. And so here's a few other things that we've seen happen over the years. If we haven't properly fastened those baskets to the grade, you can see if those dowels start to float to the surface, they're not going to provide the load transfer that we want. And so this is something that can happen if those dowel bars start to tip at all or kind of get skewed at all and get too close to the surface. We want those dowels at mid-depth of our pavement as much as possible. In reality, if they're in the middle third of the pavement, they're still going to do their job, but if they're too close to the surface, then we're going to cause issues in the surface of our pavement. And so going back to that concept of basket rigidity, this is one of those reasons why we recommend leaving those shipping wires intact, trying to avoid a basket that's falling apart. And I get that that's not the best picture, but it's really kind of hard to try to get good pictures of this during the middle of paving. So as you can imagine, it's kind of a challenge to see. You'll also notice on that picture on the right where the dowel has actually just slipped out of the basket itself. Again, if we have those shipping wires intact, that tends not to be an issue because those baskets aren't going to open up during that paving process quite as much. All right. Shifting to our other type of pre-placed steel, when we're placing tie bars within our pavement, you can see how those are kind of laid out. One thing that we should be mindful of is that we don't want those tie bars too close to our dowel bars if we're having dowel bars in our transverse joints, because that's a good way to lock up a corner, and then it can very quickly lead to corner breaks within our pavement. And so we want to keep at least 6 inches off of the tip of the nearest dowel bar to make sure that we don't get that negative interaction. If we have something like this, then we're probably way too close to the end of that dowel bar, and likely going to lock up that corner, which will again likely lead to corner breaks or corner cracking off of that on that slab. All right, so moving right along with construction, the next thing we want to be mindful of is when do we saw those joints? And so to understand that, we have to think of this concept of a sawing window. Our concrete has to have gained enough strength that it can resist the kind of saw going through it, and it'll, rather than just pushing the aggregate around and causing raveling. So if we're too early within the sawing window, the concrete hasn't gained enough strength, and it's just going to shift aggregate around. And so we're not going to get a nice and clean cut. So too early and we get raveling. If we wait too late within the sawing window, then your concrete strength gain is starting to compete with your stresses that are developing within that concrete. And if the stress hits the point of the strength, that's when we're going to get cracking. So that kind of defines our sawing window. And this sawing window is going to be impacted by quite a few different factors. So giving you a time isn't really the way that we can do this. So we have to understand the factors that will really change that sawing window. So we've got weather. It's very dependent. Your concrete's hydration is going to be very dependent on the weather that it's being placed in, especially the heat, the humidity, even sunshine itself will change how it gains strength over time. Additionally, it'll be dependent on the subgrade or subbase that we're placing our concrete on. Some of that can steal moisture out of our pavement. Additionally, how hot that subgrade or subbase is will change how our pavement hydrates over time. So that will impact the sawing window as well. Other things that will impact it, concrete mixture, that's going to change how quickly our pavement hydrates, as well as if we're paving next to a lane that's already been paved, that will also change how our concrete hydrates over time. So all of these things can impact that sawing window that we've already kind of just defined. But the biggest thing that will impact our sawing window is curing. If we have proper curing of our concrete pavements, it is going to keep the heat and the moisture within our pavements and properly hydrate that cement. And so if we do that appropriately, it's going to basically lead to our concrete gaining strength more quickly, and it's also going to delay the onset of that development of stress within our concrete. So it's actually going to change both ends of that sawing window by keeping the heat and the moisture within our concrete pavement. So this is kind of what that does to shifting around that sawing window. We've basically kind of improved how our concrete is gaining strength. We've also delayed the onset of that development of internal stress, and so we've lengthened that sawing window. And so there is research that's being done to try to make sensors that will more accurately define this sawing window, but we're not quite there yet in terms of having good quantitative data on basically every concrete pavement of how this sawing window develops over time. Having said that, there are tools that can be helpful for evaluating this. One is the evaporation rate calculator. This will help give you an idea of how much moisture you're losing from your concrete pavement based on your ambient temperature and a few other factors. And so this can be very helpful in defining some of that sawing window. There's also a tool called HyperPave, which is also very helpful in defining, in understanding that sawing window and how it's going to change over time. But as I was kind of talking about that sawing window, if we get on our pavement too early, the raveling that I'm talking about is exactly what you'll see in that top picture there. If we're in that moderate range, we're probably okay. If we're in the none range, I mean, yeah, that looks like a nice tight joint, but we want to make sure that we're not so late in that sawing window that we're going to risk random cracking. So, got to be mindful of all of that. And now it's not just about sawing our joints at the proper time. We also need to make sure that we saw them at the proper depth. So you can see here that picture on the left is a longitudinal joint where we just did not saw deep enough. So you can see the saw cut's clearly there, but if we don't saw deep enough, we're not going to activate that joint off of the bottom, or activate that joint with crack off the bottom of the saw cut. So we got to make sure that we saw to the proper depth as well. You can see the transverse joint there on the right as well. Clearly have the saw cut in there, but if it's not deep enough, it may not activate that joint. And so our general recommendations for transverse joint is 1/4 of the thickness for pavement being placed on an unstabilized base, 1/3 of the thickness if we're on a stabilized base, just to make sure that we properly activate it. Longitudinal joints, T/3 is a general recommendation, primarily because we're not as concerned with load transfer at those longitudinal joints as we are with our transverse joints. If we are using early entry saws, we're likely going to be a shallower cut, but if we do start to see dust coming up from that saw cut, we're gonna wanna go back over to T/4 to make sure we activate that joint. And so you can see the difference between that conventional saw cut and an early entry saw. Both can work very well, but you can also see the amount of aggregate interlock that we'd have with the changing depth of those saw cuts. Okay, actually I do want to mention one more thing with this. So when we're out there and we're sawing our joints, it is ideal to saw every joint successively. We want to make sure that we're activating every single one of those joints. If we do skip sawing because we're getting late in the sawing window, it may relieve some of that stress, but it is a recipe for creating dominant joints, or joints that really open up and close a lot more than every other successive joint. So we want to activate every joint successively as much as possible, such that we get these nice tight cracks rather than having cracks that open up quite a bit. All right, so real briefly, I want to talk about joint sealing. I will mention there is a good resource on joint sealing from ACPA that covers all of this. There has been a shift from conventional sealing with backer rod and sealant to kind of just filling our joints. And part of the reason behind that is to try to keep joints tighter, or the saw cuts a little bit tighter, but also because a lot of agencies, what we've seen across the country is that they're not doing a good job of maintaining these joint seals, and so filling can be something that's less maintenance heavy and can still kind of reduce some of the moisture and incompressible infiltration over time. So that is what joint sealing is really for. We're really trying to keep as much moisture out of our joint system as possible, as much incompressibles out of our joint system as possible. We're never going to completely stop those things, but if we can minimize them as much as possible, it is going to lead to better performance, primarily because moisture will help erode things underneath our pavements, especially at those joints. And so we want to try to keep as much water out as possible. Now, again, having said that, moisture is going to get into our pavement system from a number of different mechanisms. It's not just coming in from the top, and so we can't really control every aspect of keeping moisture out of our pavements. But if we do seal our joints appropriately, we can minimize it a little bit from the top. And so if we don't seal our joints, or if we do a poor job of maintaining those seals, some things that we can really see are buckling or blow-ups, like you can see here. And that primarily happens as we start to get incompressibles and a lot of moisture into those joints. As they try to expand and contract, they will get to a point where they have to relieve stress because there's so much buildup of stuff in those joints, and we can get failures like this. And so a lot of times that happens when we've got a lot of stuff in those joints, and then we get a lot of rain at one point, and then we get a hot day right after it, and it'll expand things, and there's no room to expand, and so we can get those failures that you see up there. And so the few different types of sealants, we've got the hot pour sealants, we've got silicone sealants. Some states are also using compression seals, although we do see that more on the aviation side. All of these can work, but they do have different life expectancies and costs that are associated with them, but they are the types of sealants that we have. And so you can see a little bit of a schematic of what these can all look like. If we've got the single saw cut and we're not sealing or filling our joints, you can see that far left one. If we're just filling our joints, a lot of times we'll have a single saw cut and then fill from the bottom up. We've got filled within a reservoir where we come back in and do a reservoir cut for that sealant. And then if we're doing conventional sealing with a silicone sealant, you can see we've got a backer rod in there in that reservoir cut, and then we're coming back in with that silicone sealant and being mindful of the depth to width ratio, which is the shape factor for that joint sealant. And then we've got our compression seals, which are kind of designed to stay in compression for the entire life of that sealant. All right, so now we get to the fun stuff, which is joint layout. And so as I mentioned earlier on, concrete likes to stay in nice squares. And so if we're doing a long section of concrete, 15 foot by 12 foot, things are nice and easy. It's as square as possible, it's a little rectangular, but it works really well. What becomes challenging is when we have complex geometries like intersections, roundabouts, diverging diamond interchanges. Because of the curvature and the nature of those designs, we're not going to be able to keep everything nice and square. So laying out our joints in a way that's going to minimize kind of distressed development is kind of the main goal of this. So anytime we're thinking about joint layout for complex geometries, here's some things that we want to be mindful of. We want to match our joints in type and location. So on there, you might notice that we've got a crack. We want to match that with a joint. Otherwise, that crack is going to propagate into our new section of concrete. If we have an isolation joint, we should carry that all the way through our pavement. Additionally, we want to place our joints to meet in pavement structures or objects. If we have a manhole or an inlet or anything like that, we want to match that with our joint layout as well. We want to isolate things that need to be isolated, and we want to keep in mind that maximum joint spacing, which is typically about 15 feet. It might be a little shorter for thinner pavements. And then we need to be mindful that some of these joints may need to be adjusted when we're out in the field. If we have if we have an intersection and we're kind of laying out our joints in the office, what's out in the field may not perfectly match what's on our plans, and so we need to be mindful that those joints might need to be shifted as we go through the paving process. Some things that we want to avoid as much as possible when we're doing intersection, roundabout, diverging diamond joint layouts, we want to avoid any slab that gets too big or too small. If we have a slab that gets very narrow, like 2 feet wide or less, it's a recipe for getting cracking, primarily because we're not keeping things as square as we could. We also want to avoid any slab that gets too wide. If we're getting greater than 14, 15 feet, it's going to be a recipe for getting a longitudinal crack, like you can kind of see in that second picture there. It's one of those examples where our slab got very wide, but it was kind of borderline. In the next picture right below it, you can see the very similar intersection, but we just bisected that slab to keep it a little bit more even in terms of size and reduce from that 15 feet, and we can get better performance. We also want to keep things as square as possible. We want to avoid any angle that gets less than 60 degrees. Keeping things square is going to be best, but obviously we're not going to be able to keep everything square when we have all of the curvature that we have in an intersection. And we want to avoid odd-shaped slabs as much as possible too. All right, so now we're going to go through a 10-step method for how to lay out the joints for intersections that works really well for just about any type of intersection. You can see both a skewed T intersection as well as another conventional four-way intersection. And this is kind of a process for laying out our joints that makes this a little bit easy. So step one, we get our bird's eye view of our intersection, draw all of our edge of pavement and back of curb lines in our plan view. Step two, we add in some circumference and taper return lines. So anytime where we have some curvature within our pavement, we're going to add a little offset, about 1.5 to 3 feet. Doesn't really matter. Somewhere in there, we're going to add a return line such that we don't have sharp angles later on. So step three, we're going to draw all of our lane lines in the main line roadway as well as the crossroad. We're not extending these through those return lines that we just added. Step four, we think like a contractor. If I can get a slip form paver in here and utilize that machine, it's going to likely give me a smoother pavement, and also it can change the efficiency of how quickly I can build this intersection. And so this is where we would kind of think of how we might slip form pave this section and carry that through there. In step five, we start adding transverse joints. And the first transverse joints we're going to add are anywhere where our pavement width changes. So anywhere where we've got at the start of a curvature, we're going to add a transverse joint. And so those are the first transverse joints we add. Step six, we start adding the rest of our transverse joints out of the central portion of our intersection. And so again, here we're going to be mindful of our maximum joint spacing, try to keep things as consistent as possible. Step seven, we define our intersection box. This happens by extending the edge of our pavement lines into the central portion of our intersection. You'll notice that everything within there stays nice and square, which is exactly what we're looking for. Step eight, we check the distance between that intersection box and the next transverse joint, and then we decide whether or not we need more transverse joints within there, which is step 9. And then step 10, we start to clean up those edges of our pavements and deal with some of those odd-shaped slabs. And so as you can see, this 10-step process really takes those odd-shaped slabs and gets them out of the main traveled way as much as possible, and it keeps everything as square as possible within the main portion of the intersection. And so just some details on how we can deal with some of those odd-shaped slabs and what to do when we run into some of those cases where we have sharp angles or a slab that's going to have that's going to be very narrow or anything like that. Some good details of geometries that will work fairly well. So a few things that we will run into when we're doing this, you can see a lot of times when we have these types of geometries, we will have a dead end joint or a longitudinal joint that at some point we have to stop. Otherwise, we're going to have a very sharp angle or a very narrow slab. So if we have a dead end joint, there are a few different ways that we can deal with this. You can see the one on the left, we've just added some rebar there off of the end of that dead end joint. That makes sure that as we get a sympathy crack into that next slab, it's held nice and tight and it won't propagate all the way through that next slab. The other option is to core or form a hole at the end of that dead end joint, and that'll make sure it arrests that crack and doesn't propagate into that next slab. And so you can see what that kind of looks like where we've actually taken a form for a cylinder and cut it up and then actually paved around it, and we just take that out, and then we can fill that hole with some low strength repair material, and we can get good performance out of that as well. And so then the last thing that we should be looking at with our joint layout is to adjust our joints for utilities and any in-pavement objects. And so anytime where we've got a utility, or within 5 feet of our joint, we should adjust that joint layout just a little bit such that we can meet those in-pavement objects. You can see some box out details that we would have. A lot of times we're going to have an isolation joint around those to make sure that we can deal with some of the vertical movements that we might have with that fixture. It's going to move a lot more vertically than our pavement would. We want to isolate that movement such that we can get better performance. A lot of times using a telescoping manhole that doesn't have that vertical movement will lead to a really good performance as well, even without having isolation joint around it. And so you can see if we box things out appropriately, we're going to get good performance. Again, just adjusting those joints a little bit such that we can meet those objects will lead to good performance. If we don't consider them with our jointing plan, that's how we get cracking, like we can see here, where we should have just adjusted our joints a little bit to get better performance. Isolation joints, a lot of times we will have isolation joints within an intersection, especially when we're looking at roundabouts. But here we need to be mindful of kind of having opposing forces within our intersection, especially when we have T intersections and there's nothing on the other side kind of resisting that expansion and contraction. That's when we want to be mindful of having an isolation joint there to deal with some of that. And so ACPA has a number of different documents that can help with jointing, especially intersections. We've got a good intersection guide. We've got a new guide that's going to look at intersections and roundabouts that's almost done, but it's a good resource as well. But this 10-step method works for other geometries. You can see an example here of a kind of a rest area, and you can see this can work really well for dealing with some of those odd-shaped slabs and getting them out of the main traveled way. ACPA does have a few other step-by-step guidance for roundabouts as well as interchanges. I think I've got the roundabouts one in here, but these step-by-step methods are really to help with the jointing process to make it easy to get those odd-shaped slabs out of the traveled way as much as possible. With the roundabouts one, we don't want to joint like a typical intersection, primarily because that's when you get stuff like this where you get a lot of cracking and it doesn't really guide users through that roundabout. And so we try to do stuff like this where we've got either an isolated circle on the left or a pave through. Both of these can work really well, and our 6-step method kind of goes through this process of laying out our joints and then kind of defining where those isolation joints go, laying out our transverse joints, and all of these should be kind of radiating out from the central portion of that intersection, being mindful of the maximum joint spacing on that outside of the edge. If we do have to mismatch our joints within the truck apron, we can do that with an isolation joint. And then, again, adding transverse joints where our pavement width changes, keeping in mind that maximum joint spacing, and then adjusting for utilities as much as possible. So anytime where we do have an odd-shaped slab within a joint layout, whether it's an intersection or a roundabout, adding a little bit of reinforcement in there is a good idea to help make sure that if it does crack, those cracks stay nice and tight and don't degrade over time. And so you can see exactly this is a roundabout where we've got that odd-shaped slab. It's likely to crack there, so having some reinforcement is a pretty good insurance on that. There are different methodologies for intersections and roundabouts. This is an example of a pinwheel method. So there are other ways that we can joint these things. The step-by-step methods are just a good strategy to help get through that process fairly simply and fairly easily. This is what that 11-step method looks like for DDIs, or diverging diamond interchanges. It's available for free on ACPA's WikiPave site, so it is out there. You can find it just by Googling. It's a really good resource that's out there for that type of facility. And so I want to finish with this picture. The step-by-step jointing method is really there to help make sure that we don't get issues with these joint layouts, because it will impact the long-term performance of our intersections. This is an example of an intersection joint layout that I received, and they asked me to comment on it. I'm like, yeah, there's no way we should be building that. So if we follow the 10-step method, it will avoid a lot of the things that you can see here with mismatched joints or sharp angles or really narrow and long slabs, and that's what we're really trying to go for. Trying to get good long-term performance concrete pavements out of those intersections and DDIs. And so with that, I think I'm right on time. Thank you guys for your attention. If you have any questions, I'll be around. If not, thank you.
All right. All right, well, you guys already beat me to asking for the round of applause. We do have a quick minute or two here for some questions.
Eric, thank you for the presentation. It was very thorough. I appreciated the fact that you emphasized trying to maintain pavement widths going through the intersections for the pavers. I know Northern Improvement has some people here, and from a paving standpoint, anytime we can have those consistent lanes, it's extremely important so we can pave through those intersections. And it's not just for the speed and the price. I mean, it's cheaper, it's faster, but it's also better. Anytime we can use a slip-form paver, we're getting better consolidation, we're getting better air void matrix. There's just the positives are endless. So yeah, and changing a paver over, a lot of people don't understand that with a slip-form paver, it's going to take a couple days to add 2 feet or something along those lines. So no, I really appreciate that. Thank you.
Absolutely, that's a great comment. That's one of the big benefits of thinking like a paver. I know it's not natural for us, but thinking through how that thing is going to be constructed is important to making sure that we get good performance and to expedite the construction and get better quality. So, great comment.
Hello, my name is Suleiman Koistani and I'm working with the city of Williston. I have a question regarding the rehabilitating of the older pavement with the joint filler. When is the best time to replace the section or repair the joints?
Okay, so when is the best time to repair the joint sealants? Is that what we're talking about?
Yes, when is the best time to replace the section or repair the joint?
Okay.
What factors are we have to consider when we deciding to replace the joints or the section or repair the joint?
Okay, so when I think I got your question now. So when we're having issues with our joints or issues with our slabs, we need to be mindful of how extensive those issues are. If we're having, 20, 30% of our slabs that are cracked, then is it going to be economical to do a big repair job, or are we going to, or is it going to be more economical to do an overlay or something like that? And so there is good guidance on that within the pavement preservation guide from the CP Tech Center, and it'll kind of give you an idea of what you need to consider for should I do a big repair job or should I do more extensive rehab or an overlay or reconstruction. I don't have a good rule of thumb on what that boundary is, but it really comes down to the economics of how much are you going to have to repair, or are you going to be able to do, and how long will that repair actually last. So if there are extensive issues within a pavement, we got to ask, are those isolated or is it pervasive and our concrete has just reached the end of its life and we're likely going to continue to see more and more issues. So a lot of times if we get on our pavements early enough and we've dealt with those issues periodically through the pavement's life, we're going to get better performance and do better job preserving those pavements than if we wait a long time and then we get pervasive cracking throughout the entire job. So it's kind of that balance of that. But I would really recommend the pavement preservation, the concrete pavement preservation guide from the CP Tech Center. It's a good resource for exactly what you're talking about.
All right. Well, we are running up on time here. I'll let you ask your question, but if anybody has to get going to or fro here, please feel free to come and go as you please.
Say, does the material that's used for the support, like let's say I have a regular rebar that's metal in comparison to like fiberglass rebar, does that change saw cut distances?
That's a good question. It shouldn't really matter the saw cut distances depending on the type of steel or reinforcement that we're putting in there. It shouldn't really change our saw cut recommendations. That stuff's in there to serve a purpose, whether it's keeping that joint nice and tight or, again, if it's on the dowel side, making sure that we get good loan transfer. So it shouldn't change our sawing or our joint spacing recommendations.